Let's talk about composing functions and then looking at their domains. So first, let's just compose them. Let's look at f of g of x first. So f of g of x is going to be written as f of g of x. So that's just f of, and g of x is square root of x. And that's going to become square root of x squared. So I'm going to leave it like that for now. On the other hand, g of f of x would be g of f of x, and that's g of x squared, and g takes inputs and square roots them, so it's the square root of x squared. And then lastly, h of g of x which we write as h g of x, which is h of, and g of x is the square root of x, and then h takes things and square roots 2 minus that thing. So this is square root of 2 minus square root of x. Alright, so there's our functions. Let's talk about the domains. So, the reason this is important is because it can be tempting to do this. So you don't want to do this necessarily. So this is definitely equal to x squared. So it's tempting to look at x squared and say, well, the domain's negative infinity to infinity, because we know the graph of x squared. It takes all x values as inputs and produces real valued outputs. The problem is this is a function that's being composed, and so in order to even get to that output, we have to make sure that the values that are being fed into g can actually get sent to outputs in f of g of x. So, for instance, if I took something like, how about negative 2. When you do g of negative 2, you take the first thing you're going to do is take the square root of that, and the square root of negative 2 doesn't exist. So f can't take the square root of negative 2 as an input, because the square root of negative 2 is not a real number. So negative 2 is not in the domain of g of x, so it can't be in the domain of f of g of x. So that suggests that we should probably look at the domain of the inner function first. So look at the domain of g of x. Well, g of x is the square root of x, so you can only take square roots of numbers that are bigger than or equal to 0. So the domain of g of x is 0 to infinity. And so just think about what happens after that. When you take a number and square root it, you just get a positive number, or 0. And then what are we going to do after that? Well, f is going to square those things, so there's no issue there. So that means that our domain of f of g of x is just 0 to infinity as well. In other words, all those inputs that we put into g are going to get sent to outputs in f of g of x. Right? All numbers from 0 to infinity that you put into g will find an output when you put them ultimately into f. On the other hand, let's look at g of f of x. So here, again, it's tempting to just say that this is equal to x, which it is, and say that the domain is negative infinity to infinity, and it may well be, but you don't want to jump to that conclusion right away. Let's take a look at the domain of the inside first. So the domain of f of x, well, f of x takes things and squares them, and you can do that with any number, so that domain is negative infinity to infinity. And then what does g do? Well, it square roots things. Now, when you input a number into f of x, it's going to square them, which means you're going to get all positive numbers, or 0. And then we're just going to be square rooting those guys. So you can square root numbers that are equal to 0 or larger, and that means that all these guys in the domain of f are going to find outputs when you compose these two functions. So that also means that the domain of f of g of x, of g of f of x g of f of x. Also happens to be negative infinity to infinity. So now let's look at this last example. Here I've got that h of g of x is the square root of 2 minus root x. So again, let's look at the domain of the innermost function, because we got to make sure that those inputs, we got to make sure we can at least take a look at what inputs can actually go somewhere when we input them into the inner function. So the domain of g of x, so we've already looked at the domain of g of x, that's 0 to infinity. Now, what about the domain? So is that the domain of h of g of x? Well, let's think about what happens here. We're going to be taking these numbers from 0 to infinity, and we're going to take the square root of them. Now, when you take the square root of those guys, you get you'll get positive numbers or maybe 0. However, not all of those guys are going to produce outputs when you then put them into h. So just as an example, let's try, let's say we input, I don't know, 64. So let's say I did h of g of 64, right? So 64 is definitely in the domain of g, right? It's in the domain of g because it's on the interval 0 to infinity. So we'll get an answer out. That's h of, and the square root of 64 is 8. However, I can't really put this into h now, because look what h does. H says take the square root of 2 minus x, so that's going to be the square root of 2 minus 8, but that's not a real number. So 64 is not in the domain. It's not in the domain of h of g of x. So, in this case, the domain of h of g of x is not just the domain of g of x. We're going to have to limit that. So how do we analyze that? Well, I would just say go take a look at your innermost function here, right? H is ultimately going to be taking the square root of 2 minus the square root of x. Now that number, that output needs to be 0 or bigger. Right? So we need this to be, we want that 2 minus the square root of x to be bigger than or equal to 0. Or else you wouldn't be getting a real valued output. But that means that if you add square root of x to both sides, 2 is bigger than or equal to the square root of x. And squaring both sides means that x is less than or equal to 4. So, in order to input something into h, we need x to be less than or equal to 4. And so if we combine these two ideas, we see that the domain of h of g of x is going to be, well, if you combine that, it has to be from 0 to infinity, but also less than or equal to 4. We see that it's 0 to 4 inclusive. Sometimes you need to take a look at a function and see if you can decompose it into two different functions. So for instance, if I have h of x is equal to f of g of x, and h of x is this, the question is, can I come up with two guys, f and g, so that it was as though we composed those two to create h? So one thing I might notice about this in particular is that a lot of times with functions you have what's notably an inside and an outside piece, right? So I would look at this function and say, what am I doing? What does h do? It takes the square root of things, kind of broadly speaking, and in particular it takes the square root of things of the form x squared minus 3. So that x squared minus 3 suggests that that's the inner function that we're actually putting into another one. So I would probably say, well, I'm going to take my g of x to be, since it's on the inner part, I'm going to take that to be x squared minus 3. And I'm going to take my f of x to be the outside. So my f of x would be taking the square root of something. So I'll be writing it as the square root of x. And you can check by doing f of g of x and that's going to be f of x squared minus 3, and then f takes things and square roots them. So we're right. Again, notice if you had reversed it, if you had said that f of x was equal to x squared minus 3, and g of x was equal to square root of x, then what you would have gotten is the wrong answer. And that just suggests that function composition is not commutative. So if we do f of g of x in this case, you'd get f of g of x as a square root of x, and then feeding that into f, you get the square root of x squared minus 3, or x minus 3, which is not what we see above there. All right, so again, function composition is not commutative, and in this case it's evident if you check after you decide which function to be the inner and the outer, you should be able to see if you did it right. One thing that will always work, and this is a trivial example. I'll just call this the trivial decomposition. The trivial decomposition would be to take something like this and say, I'm going to let g of x be the whole thing, and I'm just going to let f of x equal x. The reason that'll always work is because f of x equals x is called the identity function, and all that does is just leave things unchanged. It returns whatever the input was. So for instance, f of g of x in this case would be f of square root of x squared minus 3. And what does f do? Well, it just takes whatever the input is and spits it back out. So this would work too, but I call it trivial because it's not as interesting as probably the one above. Composing functions can help us see if two functions are inverses of each other by the inverse composition rule. So two functions are inverses if you compose them and you always get out x, whatever the input was. So specifically, f and g are inverses if f of g of x equals x for all x in the domain of g, and also g of f of x is equal to x for all x in the domain of f. So this can be used to figure out if two functions are inverses of each other without actually taking a function and then finding its inverse directly. So for instance, if we need to show that f of x equals x cubed and g of x equals the cube root of x are inverses, we can just compose them. So compose them both ways. F of g of x would be f of the cube root of x, and that's going to be, so f cubes things, so it's going to be the cube root of x cubed, which is x. So it worked for the first one. We got to check the other direction. G of f of x is equal to g of cube root, x cubed. And then g takes the cube root of things, so it's going to cube root x cubed. And the cube root of x cubed is just x. So f of x and g of x are inverses of each other. As one last final example, we can show that f of x is its own inverse. And we can do that by just saying, by composing f with itself and seeing that we get out x. So f of 1 over x would be f of x. And then what does f do? It takes inputs and takes their reciprocal, so this is going to be 1 over x, but that's just the same as x. So f of x equals 1 over x happens to be one of those functions that is its own inverse.